Today, we're going to talk about something huge, literally planet-sized. We're diving into plate tectonics. You know, it's pretty much the theory that explains, well, everything. From the highest mountains to the deepest oceans, and yep, even the ground that's moving ever so slowly right under our feet.
So, have you ever done this? You're just staring at a world map, and you notice something kind of weird. Like how the bulge of South America seems to just perfectly tuck into the curve of Africa? Well, guess what? It's not your imagination. That little observation is the first step to understanding one of the most powerful forces on our planet.
And it's so much more than just continents fitting together. It's what you'd call a great unifying concept. Why? Because it takes all these seemingly separate ideas like continental drift, the seafloor spreading, even where earthquakes and volcanoes happen, and it ties them all together into one single, elegant and dynamic picture of how the Earth works.
So here's how we're going to break it all down. First, we'll talk a bit more about this unifying theory. Then we'll get into what a tectonic plate actually is. After that, we'll map them out, see what's making them move, and finally, we'll wrap it all up with an incredible case study, the journey of the Indian plate.
Okay, let's get right to it. What are we really talking about when we say tectonic plate? Let's lay down the ground rules for how our planet is put together. So, a plate isn't just a continent, and it's not just the ocean floor. It's this massive, jagged slab of the Earth's lithosphere, which is just the rigid, rocky outer shell of the planet. And the key thing is, these giant puzzle pieces are often made of both a chunk of a continent and a piece of the ocean floor.
The whole theory really boils down to three fundamental rules. First, new crust is always being made at these things called mid-ocean ridges, while old crust gets recycled back into the Earth at deep ocean trenches. Second, because of this, the Earth's total surface area doesn't change. It's basically a perfect planetary-scale recycling system. And third, the moment that new crust is born, it becomes part of a plate. Simple as that.
So, we know what they are. Now let's meet the main players in this global game. It's time to actually map out the pieces that make up our world.
Now, the Earth's surface is mostly broken up into 7 of these major plates. These are the titans, the real heavy hitters, like the massive Pacific plate or the Eurasian plate, carrying our continents and oceans on their backs. So let's see how they all fit together.
And here they are. You can literally trace the seams of our planet on this map. Those lines are where all the action happens. The earthquakes, the volcanoes. Just look at the sheer size of the Pacific plate. It's an absolute behemoth, covering almost the entire Pacific Ocean.
But wait, it's not just those big 7. The puzzle's a little more complicated. There are also a bunch of minor plates, like the Cocos plate over by Central America, or the Nazca plate right next to South America. These smaller guys are constantly moving and interacting, and they are just as important to the whole system.
All right, so knowing the pieces is one thing, but the real mind-blowing part is that they're all moving, constantly. So what's the engine driving all this? What's going on under the hood of our planet?
Okay, here's the secret. These giant, rigid plates are actually floating on a hotter, softer, kind of gooey layer below called the asthenosphere. And they're not just drifting around randomly. They're being pushed and pulled by these massive currents of heat rising up from deep within the Earth's mantle. It's basically a giant, super slow-motion conveyor belt for continents.
So how fast are we talking here? Well, at the very slow end of the spectrum, you have the Arctic Ridge. The plates there are spreading apart at less than 2 centimeters a year. To give you some perspective, that's about the same speed your fingernails grow. So, not very fast.
But then you go to the other extreme, like the East Pacific Rise. Here, the plates are racing apart at more than 15 centimeters a year. In geological terms, that is absolutely flying. The difference across the globe is just staggering.
This chart really helps you see it. On the left, you've got the snail's pace of the Arctic Ridge. Then, in the middle, Australia is trucking north at a pretty respectable 5.6 centimeters per year. And then, whoa, look at the right. You have the speed demon, the East Pacific Rise, moving more than 7 times faster than the plates in the Arctic.
Now, to really understand the incredible power of this movement over millions of years, we're going to zoom in on one of the most dramatic stories on Earth, the epic, unbelievable journey of the Indian plate. I mean, just look at this. This shows a landmass that was once a giant island way down in the southern hemisphere, just cruising north across an entire ocean to eventually slam into a whole other continent. I promise you, this isn't science fiction. This is the real history of our planet. So let's follow the journey.
It kicks off around 200 million years ago, with India as a big island. Fast forward to 71 million years ago, and it's still way south of Asia, just adrift in the ocean. But then, between 40 and 50 million years ago, it happened. The big one, the collision with Asia began.
And the result of that colossal, slow-motion crash? Only the creation of the Himalayas, the highest mountain range on the entire planet. The immense pressure of one continent smashing into another literally buckled and folded the Earth's crust, forcing it miles up into the sky to create the roof of the world. And if you think that's incredible, get this. It's not over. Scientists are pretty sure this whole process is still going on. The Indian plate is still pushing, still grinding into the Eurasian plate. And because of that, right now, as you're listening to this, the Himalayas are still getting taller. So that leaves us with a pretty wild final thought, right? The same forces that drove an island across an ocean and built the world's tallest mountains are still hard at work today. The ground beneath us isn't static. It's a living, breathing, moving thing. So it makes you wonder, if this is what happened in the past, what will our world map even look like in another 50 million years?